What's that? Spindom. Spinning momentum. Angular momentum. Just so you guys know, you got the notes as you walked in. Those at home have the notes on the module. So I'm gonna talk about angular momentum for a little bit, show a couple short videos, and then you're gonna work on the quest assignment. We're gonna work on that quest assignment on Monday. It will be due Tuesday night. It is a major grade. Okay? But Tuesday we will be starting some new stuff. Yeah, so that's it. So let's talk about spinning momentum. Let me admit Timothy first.
Timothy!
Hey. Good
Morning.
Good morning. Everyone said hi. Not everyone, but some
I
people.
didn't say hi.
All right. So, angular momentum. Angular momentum. Yes. Angular momentum, because angular starts with the letter L. Angular momentum gets the symbol L, capital L. It is a vector. It's one of those weird three-dimensional vectors that we use the right-hand rule to determine the direction of. And the most general definition of angular momentum is for a point mass. This will be for a point mass. So we'll say angular momentum for a point mass, which is just, a mass that you can consider all its mass to be concentrated at a single point. So if an object is small enough and you're far enough distance away, then you can just approximate it as a point mass. It's equal to the position vector, indicating the position of that particle, crossed with the linear momentum of the particle, or the point mass. You remember cross product? That whole thing, right hand rule? Okay. So that's the most general definition for the angular momentum for a point mass. And so let's just kind of look at what that might look like. Let's say I have this. You need a coordinate system, because if we're drawing a position vector, we need to reference the position of the object to some coordinate system. So let's say we have this coordinate system here. And we have a mass here that happens to be moving in this direction. Then we would draw our position vector like this. And that would be our position vector R. And so the cross product of this vector and that vector will be the angular momentum of that particle. Notice, this is a tricky conceptual idea. This mass is not moving in a spinny way. It's moving in a straight line.
Yeah, I was about to ask.
Yeah.
Because I noticed last year, I was very confused. Point particles have angular momentum.
Point particles have angular momentum most of the time. You have a question?
So then it would just be 180 degrees.
That'd be what?
The angle is 180 degrees.
The angle between these two vectors?
No, just the velocity.
The velocity has an angle of 100. I don't know what you're saying.
But
I'm
why
confusing
do
you on
particles-
purpose.
Stop confusing me.
Okay.
Wait, but why do particles have angular momentum as opposed to linear momentum?
They have linear momentum, but they also have angular momentum because at this particular time, at this instant in time, relative to this point, let's call this point P. Relative to point P, this guy is kind of moving in a circle. You can think he's kind of moving in a circle. Like, if he was to move in a circle with this radius, he would be moving like this, right? And it would be kind of like that. Kind of, right? I remember I took one astrophysics class in college. And that one class told me that I wasn't cut out to be an astrophysicist. But I remember, like when he was talking about that, because it's all about angular momentum when you're talking space and like planetary disk accretion and galactic shape and stuff like that. It's all about angular momentum. And there was a girl who had that same question. She was like, but objects moving in a straight line have angular momentum, and he just kept saying everything has angular momentum. Doesn't matter if it's moving, everything's moving. Doesn't matter if it's moving in a straight line or actually spinning around something. Everything has angular momentum according to this equation. According to this equation, this object has angular momentum, right? Because you can think, at this instant in time, it's kind of like rotating about this point, right? But it's really not rotating, but you can kind of think. Now, where it won't have angular momentum is, say, relative to this point. Because relative to this point, the r vector points this way, v points that way, r cross p, because p is mv, right? R cross p would be 0, because the angle between those two would be 180 degrees.
I guess.
And the sine of 180 degrees would be 0. So relative to the line of motion, anywhere, if I pick any reference point along the actual line of linear motion, the object has no angular momentum relative to that point. But when we talk about angular momentum, at least for a point mass, our choice of coordinate system is completely arbitrary. So unless you're not along that line, any point in the universe away from that object that's not along the line of motion, about that point, this object would have angular momentum.
I guess the way to think about it is like an object, if R were to become a string or beam that it spins around point P,
Yeah.
then as long as there is velocity that would make it start to spin, then it has angular momentum.
That's a good one. That's a good one. If this guy's moving in a straight line and then at this instant we magically turned R into a string that would hold this guy, he would actually move in a circle. I like that. I'm gonna steal that and take credit for it. Does that make sense then?
Yeah.
Okay.
But if you made a beam at that point P you just erased, then it would just not actually spin.
Right. Yeah. Yeah. Because if it pointed there, then it would just yeah. No, that was good. That was good. That was good. Now the thing is he's going to continue to move in a straight line. So over here, and if he's moving with the same v, I got a new position vector, and I got a new angle, right? So I'll call this R1, I'll call this R2. But the v is the same. Now the angles here, be careful. The angle between these two vectors we can say is this. So I'll call this angle theta 1 and this angle theta 2. They are different. And some students kind of get confused. Well, the angle between these two vectors, do I have to put their tails to tails? Or like if you're ever confused about that, what you want to understand, if I took R1 and put it here and measured the angle here, this would be 180 minus theta 1, right? We all know that. What's the sine of this angle compared to the sine of that angle? What can I say?
Add them together and they'll equal 1. Isn't it?
No.
Be sine plus a cosine. Supplementary, right?
There's supplementary angles.
Yeah.
The sine of theta 1 is the cosine of 180 minus theta, right?
Let's say that theta 1 is 40 degrees. The sine of 40 degrees, using my calculator, is 0.643. And then I want to do the sine of 180 minus, so the supplementary angle, which would be 140, right? If I've done my math correctly. It's 0.643.
Oh, they're equal.
They're equal to each other.
Oh, that's.
I'm going to go talk to your pre-calculus teacher and give her an earful.
Oh, okay, that makes sense.
Yeah, the sine of supplementary and cosine of supplementary angles are the same. So it doesn't matter. If you could draw, I like drawing them like this when talking about angular momentum, and just do that angle. And the sine of that angle is going to be just fine. Because remember, the magnitude of the angular momentum, why am I talking about the sine of the angle? I probably should have written this first. The angular momentum for a point mass is the cross product of r and p. The magnitude, which I can write like this, or I can just not have the absolute value bars and not put the vector symbol, is rp times the sine of the angle theta.
Makes sense.
So those angles are definitely important. The thing is that angular momentum, just like linear momentum, is a conserved quantity. which means at this point, this mass should have the same angular momentum as it had at this point relative to this point in space.
Because they both have the same, they're supplementary, so they have the.
No, now I'm talking about the two different locations.
Oh,
So at these two different locations, this object should have the same angular momentum because it is a conserved quantity. At least if it behaves like linear momentum, which it does. It is conserved. Now I'll get different values for it if I pick a different coordinate system. Right? If I go to a different coordinate system, I'll have a different r and same v, different r. But if I'm making them these measurements from a coordinate axis that's not going to coordinate system that's not going to change its location, then this should be a conserved quantity. Angular momentum should be a conserved quantity. And it turns out it is, because as r2 gets bigger here, theta 2 gets bigger as well. So the sine of theta 2 will go down. So as r goes up, the sine of the angle goes down, exactly canceling out enough so that the angular momentum will be the same at all times. Relative to this point, even after this guy is a billion light years that way, he'll still have the same angular momentum according to this equation here.
So as r approaches affinity, sine just approaches 180?
Yeah.
Okay.
And the sine of 180 is...
So is it basically
Yeah,
like,
so as r gets approaches infinitely big, sine of theta approaches 0.
so is it basically like as long as the linear momentum is constant, then at one point the angular momentum will also be constant? Or-
Yeah.
Okay.
Yeah, exactly. If this guy's moving in a straight line, the linear momentum is conserved, no external forces. And then, relative to this point, that angular momentum will also be conserved, and it won't change in the absence of external forces. Cool beans? That's just some definitional stuff. Let's do a quick example here. I think it's on... Where did I put that? Let's just kind of have a look at it. So now I'll do it real quick. The angular momentum of a point particle, the example that's in the notes, it's kind of interesting. Because really, and I should have said this. I'm sorry, before we get there. Let's say I have a coordinate system that's right here. No, we'll prove it here. I'm sorry. I don't know what I'm doing, Gianni. I don't know what I'm doing. So let's say we have 2 points, Q, 3 points, Q, O for origin, and P. Q is at 1, 2. P is right here. And we have a particle of mass m right here, moving with some speed this way. And so we want to find the angular momentum for a 5 kilogram point mass. So the mass is 5 kilograms. Located at 2, 2, right? 2, 2. The ordered pair 2, 2. With a velocity of 2 meters per second. Constant velocity. And we want to find L at O, L at P, and L at Q. So we want to find the angular momentum at those 3 locations. Okay. So the magnitude of each one will just be the linear momentum, which is mv times r. In the case, if we're doing O first, what's r here for O?
1.
the root of 8?
Yeah, it'd be
Be the square root of 2 plus 2, square root of 8, right? 2 square root of 2. So 2 square root of 2, square root of 8, good job, times the mass, which is 5, times the speed, which is 2. And obviously we can do that in our heads. and that's 20.
And then you multiply that by
Oh, sign. I'm sorry.
then you multiply that by further 2/2.
Yeah, because we got to multiply that by the sine of 45, which is the square root of 2/2.
So it's really just 4.
So you end up, when you multiply all that out, with 20.
Yeah.
Where are the units? Momentum. Momentum is kilograms times meters.
R
Right.
times meters squared.
Kilograms times meters per second.
Kilograms times meters per second. Times.
Meters, so kilograms times meters squared per second.
So that's the units. 20 kilograms times meters squared per second.
For that.
Angular momentum, according to this point, or referenced from this point, the R there is going to be this guy. The angle is going to be what?
90.
90. So the sine of 90 is 1. So this guy is just going to be the radius, or the distance, which is 2, times the mass, which is 5, times the speed, which is 2. That's going to be 20. What that means is if I was looking at it in this context, I can take my coordinate system and shift it horizontally. Just like as m moves horizontally along that axis, I get the same values. So if I was to take this guy here and measure the angular momentum of this guy from here, I get the same values. And when we solve some more complex type of collision problems, you'll want to know that. You'll want to know that the angular momentum of this guy right here relative to that coordinate system would be the same if that coordinate system was right here, as long as the direction, the axis along which the mass is moving doesn't change its orientation. Okay. If I take P though and start moving it here, if I start moving it down, that's when I'm going to get different values, as we'll see here. Because the angular momentum about this point Q is going to be, you already know it, some of you. It's going to be the R vector, the position vector, which is 2, times the mass, which is 5, times the speed, which is 2, times the sine of the angle. What's the angle between these two? It's 0.
Oh, 0, yeah.
And the sine of 0 is 0. So the angular momentum from about that point is 0. So if I either change the location of the mass as it moves this way, or I change the coordinate system along the same direction, I get the same results for angular momentum. And it's only if you start moving in directions that are at least a little bit perpendicular to the horizontal motions, where I start getting different results. Okay. This is all for point mass. This is all angular momentum for point masses. But just like rotational inertia, you start with the rotational inertia of a point mass and then use some sophisticated mathematics in order to determine rotational inertias for extended objects. Right? We're not going to do that for angular momentum. We're not gonna do integrals to figure out the equation. I'm just going to give you the equation and yeah. So, any questions so far? I know it's kind of weird to think of objects moving in straight lines as having angular momentum, but that's the starting point, and it is true. And just realize that everything in the universe. That's what that astrophysics professor just kept saying. He just kept saying, but everything has angular momentum. Yeah, but it's moving in a straight line. Yeah, it's still got angular momentum. But it's moving straight. Yeah, everything in the universe has angular momentum.
Honestly, I'm not surprised.
Even you. You have angular momentum about the center of the Earth because you're spinning around that.
Connor,
The Earth's going around.
get your angular momentum in check. Oh, no.
Get it straight. Get it straight. Okay.
Nothing
But
surprising.
his angular momentum can be straight and still have angular momentum. So
Angular momentum is a vector, and it is a straight line vector.
Once I was told that gravity doesn't exist, I don't get surprised by anything.
Gravity exists until you get to really studying general relativity, which, if you major in physics, you will.
Yeah.
So you'll be one of the few people in the world that'll actually learn why gravity does not actually exist. Okay.
Until it doesn't.
Okay. So let's say I have an object that's spinning, like this regulation-sized hockey puck. Let's say this guy's spinning. He's got angular momentum. This is true angular momentum, as we would think, because you got a bunch of little tiny masses here that are all actually moving in a circle. They're actually moving in a circle. And so if I add up all the angular momentums of all those little masses, I get the total angular momentum. And it turns out that just like linear momentum, mass times velocity, yes, angular momentum is the cross product of r, the position of a particle, and its momentum, linear momentum. But if I have an extended object that is undergoing actual rotation, then the angular momentum is equal to, what do you think?
Rotational inertia times angular.
I times local.
I times roundy W. Right.
Level.
What do you call it?
Level.
Wobble?
Upside down.
Okay, and these are vectors. These are vectors. Remember angular velocity is r cross v. Point your fingers in the direction of the position, curl them in the direction of v, and your thumb then points in the direction of omega, the angular velocity. So the angular momentum does the same. Which means if I have a disk that's spinning, let's say clockwise, if it's spinning clockwise, pick one of the little masses there, point your fingers in its direction, that's the position. Curl it in the direction of the linear momentum, the linear velocity, and your thumb would point in the direction of the angular momentum. So this guy's spinning this way, its angular momentum vector is pointing at me. If I spin it this way, it's pointing at you. So, and think about it, that's the only way to really represent an object's rotation as far as angular momentum is with a vector that's perpendicular to the plane of rotation. Otherwise, you'd have curved vectors. They'd have to constantly be turning. But I can talk about a constant angular momentum for an object rotating at constant speed with a single vector that either is pointing, that is pointing perpendicular to the actual plane of rotation.
There is no such thing as curved vectors.
No. A vector is a straight line. Yeah.
So what about
I just see
several
what-
vectors?
What's that?
Infinitesimal.
Yeah, you can do that. You can do that, and when you learn general relativity, you'll definitely start thinking about space in that way. And yeah.
Seems
Good
like
stuff.
physics is just a slow progression of, remember what you did? Yeah, not really.
Yeah. There's a famous quote from someone I can't remember, but where they say if your physics teacher is worth their salt, then they'll tell you at the end of the year that everything that I've taught you this year is not true. Okay. So, got rotating objects. If you know the rotational inertia, which we've been dealing with for a while, and the angular velocity, which we've been dealing with for a while, then it's not a big stretch to be able to calculate the angular momentum. Again, angular momentum is a conserved quantity. It's a conserved quantity. And so you can actually have an object's angular velocity change while maintaining a constant angular velocity by doing what? What would you need to do in order to change this guy? Change an angular speed, but maintain the same angular momentum, meaning no external forces are going to be present.
Shapeshift.
Fishy.
Change the, well, if there's fishy, then there has to be external forces.
Change the moment of inertia.
Change the moment of inertia, which we do by changing the r, right? The positions of the objects, the radius of each individual. By redistributing the mass. We redistribute the mass, and we get a different rotation rate while maintaining the same angular momentum. And I'm not a big fan of the Olympics, but there is an Olympic sport where they use this, and this used to trip me out when I was a kid, because my mom would watch the Winter Olympics and the figure skaters, and they would start off rotating, and then they would just spin so fast, and I'd be like, how? I don't see them like pulling on anything or pushing with their feet. They just start spinning fast, and I'd never like, I guess I kind of had an intuitive curiosity when it came to physics because I wondered about that. I was like, and I didn't get an answer for years. And so here's a nice short.
Kept you up every night.
Every night, I couldn't, just sleepless nights. How do the figure skaters spin so fast? So here, let's watch this little video.
Timeline, Mr. Graham is a figure skater.
Actually, that's what I do in my spare time.
For decades, the Winter Olympic Games have drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
See how fast you're spinning? That's nutty.
I wonder how many of them actually use physics to calculate.
Probably none of them. I bet a lot of them know physics. And even if they don't, they have an intuitive sense for it.
And the reason
We were just talking about Mike Tyson in the last period because he just had a fight. And he's like 53. Mike Tyson, you hear him talk, he doesn't sound like a super intelligent dude. He's an amazing physicist when it comes to just intuitively knowing physics and how to deliver a strong punch with the torque that your core muscles exert on your body to get it to rotate while you're delivering that punch. Like, the dude's a genius. He's a physicist, just not a classically trained physicist, right? So you don't have to.
He was like really high.
What's that?
I heard his IQ was really high.
Yeah, he's way smarter than you would think. And he knows the entire history of boxing, like everything, all the details of it. Yeah. So we got another video we're gonna watch, but before we do that, let me just show you a little example of as a common demonstration for this kind of topic.
Your recommended videos on YouTube are interesting. You have like Turks Gazette, and then the last one you had the like time lapse to the end of the universe that I
Oh.
saw that gave me an existential crisis.
Oh,
for
nice.
like a week.
I still have that existential crisis. Okay, so I'm going to start like the figure skater with my arms out like this. And I'll start spinning, and then I'll bring my arms in and watch what happens. I get really dizzy. And obviously momentum is not conserved because there's friction here. That's creating external force, external torques that slow down the rotation. This used to be a lot spinnier, but the bearings are going up. So that's a nice little demonstration of that whole thing.
So the
You guys want
why that works the best for figure skaters is because it's on ice, and ice has basically no friction.
very little friction. Yeah. So they take the R values for the mass that are out, they bring those in, which decreases the rotational inertia, and since angular momentum is conserved, the angular velocity increases. Oh, wrong way. Spin! Why is it not spinning?
Well, angular momentum.
It's because you weren't applying a torque to it.
Oh, okay.
Conserved value of 0.
Okay. Now, anyone know about the life cycles of stars?
They're born and they die.
They're born and they die. And the biggest ones make black holes. But before they get to be the biggest, the ones that aren't quite the biggest ones, they form neutron stars. And neutron stars are crazy, crazy objects. And some of them, well, they all pretty much emit jets. Some of them brighter than others. Jets of radiation, mostly electromagnetic, and then other types of radiation. But But if, as they rotate, let me write it like this.
The stars rotate.
Because they rotate, so all stars rotate. And so when a star dies, a large star, it explodes, ejects much of its mass out into space, but a lot of the mass stays and gets compressed down into a neutron star that essentially has the density of an atomic nucleus. And so it's going to be spinning. And all the material that went into making the neutron star, all of its angular momentum will be conserved. And so because it gets so much smaller, it spins around a lot faster. But those jets that I was telling you about, they happen because of the magnetic fields, which is stuff that we'll learn about next semester. These magnetic fields are what channel the radiation jets. They channel them. Who is that? They channel these jets of radiation out of the poles, and pretty much all the time, or pretty much most neutron stars, their axes of rotation are not in line with the actual poles, those magnetic poles. And so this thing sweeps out essentially the shape of a cone with those jets. And if the Earth happens to be here and that jet passes over it, then we see little flashes of light, right? And so that's what this video is about. But essentially you have something many times the mass of the sun being compressed down into something that's like the size of Manhattan. And think if something larger than the sun is rotating kind of slowly, but then you take all that mass and cram it down into the size of a city. You imagine how fast it's going to end up rotating.
So are those things solid then?
Pretty much, yeah. Yeah, they essentially, because the reason the Earth, we have time, the reason the Earth doesn't compress into something like that, like where it squeezes all the empty space out of it, the atoms, because atoms we know are mostly empty space. It's because of the electromagnetic repulsions from all the electrons. Those forces are strong enough to prevent the gravitational collapse of the Earth. Once you get to like a supermassive star who doesn't have the outward nuclear pressure anymore, if that pressure shuts off, then you have the collapse. And there's too much mass. So even the forces, the electromagnetic forces between the atoms, it's not enough to halt the collapse. And so they collapse down even farther and squeeze all the matter together. They essentially squeeze the positive charge out of protons, like positrons get emitted from all the protons through a decay process. And so essentially you get what's a big ball of neutrons that are pretty much the density of an atomic nucleus. They'll say in this video, 1 teaspoon of neutron star matter has the same mass as Mount Everest. Right? It's pretty insane. But this gives you the visuals of what I just talked about, so it's kind of neat.
Man, that just fall right to the earth.
What's that? Oh yeah. They're nothing. Yeah, it goes straight to the bottom, and it probably oscillate back and forth a couple times. Like traveling through the rocks would provide a little bit of a drag force on it. It'd be nuts.
Just a little bit.
Just a little bit. Yeah.
That's crazy drag force.
All right.
Seems like a crime show.
Rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and the neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, the beams sweep the sky like a lighthouse. To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they rotate, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays.
So interesting. One of the types of supernovae, novae, whatever you say it, because there's different types. One happens just because a star is way too big, and when it dies, it just explodes, pretty much. But that's another type, and that's what they call a standard candle. When you have a neutron star orbiting a supermassive other star, and it's close enough that its gravity will actually pull material off of the star, and it will accrete more and more material until it reaches a critical mass, and then it will go supernova. And it always happens at the same point, at the same critical mass. And so we know the brightness of those supernova, and that's how we can measure distances. We observe those supernova in different galaxies, and we can measure the apparent brightness here, work out how that brightness diminishes as it travels to us, and figure out how far away that galaxy is based on that. It's pretty ingenious method that astronomers use too. But anyway, the point is, you take a star that might orbit, kind of different parts of it orbit at different speeds because it's a big ball of gas. But it might not orbit, revolve maybe in a half a day or so, or a day or so. But then you compress it down to something the size of Manhattan, and the things, so not all of them spin this fast, but the fastest one, I think, spins around 800 times per second, something like that. So imagine something the size of like Dallas spinning around 800 times a second. And that's how fast these things move. And it's because the rotational inertia goes down so much while maintaining the same angular momentum, so the angular velocity must go up by a huge amount. So it's like the figure skater example, but just on a whole different level.
That's like spinning so fast it doesn't look like it's spinning.
Well, it probably wouldn't. I don't know what it would look like. It'd be strange. You probably wouldn't want to be anywhere close to a neutron star.
No, you get blind very easily.
Well, you would get torn apart. Yeah. If you were close enough to actually see a neutron star, then you're probably just being ripped apart by its gravity. Yeah. So it might not be too pleasant.
And if you're far enough away to like see it well, but not really, but not be torn up, you probably get like mega cancer.
Probably. Especially, I mean, if you're in line with those jets. Now, we do see those jets. We see those jets, those flashes. And imagine, because they didn't know what those were when they first detected them. So imagine what astronomers thought when they saw these regular flashings of light, like at super precise intervals.
Oh, yeah, they literally thought it was aliens.
They thought they were aliens. And do you know what they called them whenever they first detected them?
Little green men.
LGMs. Yeah, they called them LGMs. For low green men. That was before they knew what they were. But yeah, interesting stuff. Cool stuff. I think it's interesting.
I wonder what like primitive civilization was on them.
Oh, you can't. You need telescopes to see them.
Oh.
I don't think there's any visible naked eye pulsars.
And they are kind of
Natural selection.
Hmm?
Maybe have telescopes for eyes.
Yeah, there you go.
Selection.
Okay.
Adapted telescopes.
Oh. So speaking of conservation of momentum, just like with conservation of linear momentum, in collisions, whether the things bounce off or they stick together, when you talk about collisions and angular momentum, the angular momentum is always conserved, right? Angular kinetic energy isn't always going to be conserved because it'll be converted to other types of energy, but momentum is most definitely always conserved.
So are we gonna deal with impulse with spinning momentum?
Yeah. And it's not gonna be too tough as long as you know how it works with regular momentum. So I like showing this. It's not the best, and it takes a while, so I'll be talking while it's playing. But here's a little simulation. I think I rambled too much today. I'm not getting to as much as I wanted to get to. So here I got a bunch of particles and I hit play. And they're all in motion. Some of them are moving up, some are moving down, some are moving left, some are moving right. They all have a gravitational attraction to each other. So over time, they're all going to end up clumping together. This is a closed system. In this closed system, there is a single value for the angular momentum of that entire system. And even after all these collisions and all these groupings of the particles, eventually they'll all coalesce into a single object comprised of all those masses. The angular momentum will be conserved. If you understand that, you understand why galaxies are disc-shaped and why planetary systems or solar systems, as they're forming, form in discs. And it's because, what's that?
Just like the Earth.
Yeah.
Earth is a disk.
Exactly, yeah, just like the Earth, the flat Earth. So, but if you look, you start with a big collection of gas, right? That will eventually become a solar system. Some event triggers a gravitational collapse. Well, that big gas cloud has a single value for its angular momentum. It's a single vector that points in a straight line, right? And so if it points this way, then everything will end up swirling around it this way. But in the beginning, it's not. In the beginning, it's just this collapsing gas cloud where everything's kind of moving in random directions. But when you add up all those random motions, all those random angular momentum for all of those masses, they're not all going to cancel out. There's going to be one dominating direction for the angular momentum. So if it points this way, everything tends to swirl around this way. You have collisions in all dimensions, but because the angular momentum points this way, the collisions in this direction will cause it to flatten out, right? Objects will lose kinetic energy in the inelastic collisions in this direction, whereas in the actual direction of the angular momentum vector, they'll just kind of add to that angular momentum. And so that because of the angular momentum of that gas cloud, as it compresses, it ends up forming a disk, and that disk will be its angular momentum will point in the same direction its original angular momentum vector pointed in. And so here, this is a two-dimensional representation, but the angular momentum of this solid object right now is literally the sum of all the individual linear momentums or angular momentums of the point masses that made it up. Kind of make sense? Cool. And there's a reason. It's not like random chance that spiral galaxies form, or that planetary systems form, that all the planets orbit in the same plane, right? That's not by chance. It's because of the angular momentums of those systems.
Seems like angular momentum is like one of the biggest aspects of physics.
Oh yeah, for sure.
And we live in a simulation.
And then,
Yes.
and we live in a simulation. And then you try to learn about spin, which is a quantum mechanical spin, which is a quantum mechanical quantity that's kind of analogous to angular momentum, but it's not really, which I still don't understand, but you will if you're majoring in physics.
Quantum mechanics is weird.
Oh yeah.
Who knows,
Okay.
you might end up reaching the same point you do, and just be like, oh, I'm majoring in geology.
Okay, so now check this out. One other thing I want to show you. One other demonstration. Nope, wrong way. You guys got me rambling too much today. Talking about astronomy. Okay.
Sorry.
You ever seen one of these?
A wheel? Oh.
You ever seen a wheel?
No.
They were invented a couple years ago. Are you serious? If I locked that, I'm gonna run out of time.
We got 5 minutes.
5 minutes is not enough. Whatever, that's really nice. Ever seen that? Or this? Like, I'm not pushing myself. This is, the angular momentum is being conserved. When I have it like this, the angular momentum points this way. So when I go like that, it points up. But to conserve angular momentum, I have to start spinning the other way. So my angular momentum points down to maintain zero angular momentum. Right? That is why, if you had a helicopter, don't.
Listen, high school teachers, don't forget, it is National Cookie Day.
That's why if you have a
For you in
propeller
your room during your lunch, come on by
or a helicopter,
and get your treat.
cookies
Thank
are
you.
disgusting. If you have a helicopter and it starts spinning its propellers this way, the helicopter wants to spin the other way.
That's why you have to have the other propeller on the back.
That's why you got to have that vertical propeller on the back to compensate for that. Okay. Whenever Gianni's riding his dirt bikes and he's going, I got 3 minutes, and he's going big because that's what Gianni does. He's going big. When he goes big on his dirt bike, and it's coming down nose first, and he's going to land like this, and things are going to go bad, what does Gianni do?
Lean back.
Nope. You could lean back. That might help a little bit, but there's a much easier way. Much more effective way.
Oh.
If he's going like this, the bike's rotating this way.
Spin one of the wheels.
You spin the wheels.
Yes.
You hit the gas.
Oh.
And the wheel starts spinning this way.
Oh my god.
To conserve angular momentum, the bike starts rotating that way. So this is something that motocross riders know intuitively. If they're coming down nose first, they just hit the gas and it brings them back up.
That
A little bit.
explains. I played a motocross game, and that's how they.
Does it actually work like that?
You put the gas and you start tilting back
Okay. Yeah.
slowly, and I was like, I never understood it.
Yeah. Yes, sir.
That's because Oklahoma. Yeah, I was about to say, why is Oklahoma flying?
You guys are silly. Okay. Some things we didn't get to today. We'll talk about Monday briefly, and we'll work on the quest assignment. But collisions with angular momentum. We'll talk about that on Monday, though. That's it, Timothy.